Okay, so today we are going to cover part 2 of artificial neural network. So in the video that I uploaded last week, we already covered part 1, okay, the introduction to artificial neural network. All right. So in this week lab session, we will have lab session tomorrow. So for the lab session, we will do the perceptron training. Okay. So that is what for part 1 lah. So for part 2 today, we are going to go through the back propagation learning. Okay. So So in neural network application development, okay, you have this 5 methodology that you have to follow. Okay, first we have the data collection. Okay, once we have a data collection, we do the data normalization and then the neural network designing. Okay, we design the neural network based on our data and then we do the neural network training, and after that we do the testing. Okay, all these steps it involves different formula. Okay, so let's say we have this data collection. Okay, let's say we have iris data collection. Iris so for iris class we have three different class. Okay, we have iris setosa, iris versicolor, and iris virginica. Okay, so and then for this data set, we have 4 attributes here. We have one sepal length. Second attribute is the sepal width. Third attribute, which is the petal length. And fourth attribute is which is the petal width. Okay, 4 attributes for this data collection. So data collection, we call data collection is a part of the data that we choose to be used as the training sample. Let's say for this data, for this iris data set, as you already see, it's uploaded on Column. Okay, iris data set, this one. Okay, this is the iris data set that already uploaded in Column, but I copied that and paste it in Excel so that it's easier for you to see. So you have this iris data set. We have 150 data. Okay, 150 data here. So out of this 150 data, we choose some of them to be part of the training data. Okay, so that's what included in this sample lah. Okay, so we took this sample from that data set, okay, as the data collection, as the training sample. Okay, so first thing that you have to do when you have a data collection, have a data set, first thing you have to do, if you remember the CBR, it's similar to the CBR techniques. Okay, so for the case-based reasoning that we learned few weeks ago, so in case-based reasoning, you also need to find the minimum and maximum for each attributes, right? For each attributes, you need to find the minimum, maximum. So same goes to this one. Okay, you for each attribute, you will have 4 attribute here, right? The sepal length, sepal width, petal length, and petal width. We have 4 attributes. So we have to find out of the 150 data here, what is the maximum and minimum value. So the first one is the sepal length here. Sepal length. Okay, out of all this data, what is the maximum value here? The highest number. The highest number should be 7.9 as stated in the slide lah. So let's find 7.9. Minus 7.9. 7 point, this one, 7.7, 7.2, 7.6, 7.1. Nampak mata rabun. So it should be here lah, 7.9. Okay, sepal length.
133, madam.
Huh?
133 tadi.
Line 33. Okay, wait. Ni,
100.
103.
33.
133.
Uh,
Okay, ni. This is the maximum value for sepal apa? Sepal length. Okay, maximum value for sepal length 7.9. And then in that same column also you find the minimum value. Okay, for sepal length, which is 4.3. And then do the same for other attributes also. Attribute 2, 3, third and fourth. For sepal width, you find the maximum and minimum value. For petal length also minimum and maximum value, and the petal width, the maximum and minimum value. Okay, so let's say you are given the new data here. The new data, okay, you have the value of sepal length, you have the value of sepal width, you have value of petal length and value of petal width. You have to do the prediction of this. You have these attributes in which iris class it will fall into. So we have three class, right? We have iris setosa, iris versicolor, and iris virginica. So you have to define which iris class that have these attributes, which class it will fall into. Okay, you are trying to do the prediction. Lebih kurang macam what we did in the CBR, right? We have attributes. We want to predict given the water level. We want to predict if the gate of the what is that empangan going to open or close, right? Same with here lah. We are going to predict the iris class given the attributes. Okay. uh, so that's why if you are given a question, okay, if you are given a questions to do prediction, let's say, so you have the choice either to answer with CBR, CBR method, or you can also use uh, ANN method. Okay. So let's move on with the steps here. So then data normalization. Okay, data normalization basically is a process to no to apply to do the normalization on the selected data. Okay, on the selected data. So we have the maximum and minimum normalization formula here. Okay, so for this formula, let's say we want to normalize data that range between 0 to 1. Okay, so we will have a new maximum, which is 1, and the new minimum, which is 0. So let's say we want to, what is the value of V here? V is the value that we want to normalize. Let's say we choose any number from our data set here. Let's say we want to normalize this value, okay, 3.3. So V will be 3.3. 3.3 minus what is the minimum value for that attribute. Minimum value for that attribute. Let's say it's sepal width. Okay, the minimum for sepal width over maximum for sepal width minus minimum of sepal width. Okay, and then dalam kurungan here, new max A. New max here, as given in this example, 1. Okay, 1 minus new minimum 0. Okay, minus 0 plus new minimum, which is 1. And then you will get the normalized value for that specific data. Okay, that's what we call as the data normalization. Okay, so let's move on to the neural network design. So once you already have data collection, you do data normalization, you will design the neural network. Okay, so we have 4 attributes. Okay, we have 4 attributes. We have sepal length, sepal width, petal length, and petal width. And then we have one decision to make here, one prediction. the iris class. Okay, given those attributes, what are going to be the iris class for those attributes? Okay, that's why we will have four input nodes here. Four input nodes that we refer to the four attributes. Okay, and the output layer is our prediction result lah. The output here, prediction result. Uh, either it's gonna be the iris setosa, iris versicolor, or what is that? Iris setosa, iris versicolor, or iris virginica. Okay, three kind of potential output. Okay, so this is the network design lah. Okay, so you have four attribute. Okay, sepal length, sepal width, petal length, and petal width. Okay, you have two hidden layer, and then one output layer. Okay, so forward propagate. Forward propagate is like how we move from input all the way to output. That's what we call as forward propagate. So for forward propagate, okay, we can calculate an output from a neural network by propagating an input signal through each layer using the output layer values. Okay, so that's what we call as forward propagation. We move from input to hidden layer to the output layer. Okay, so this technique, we need to generate the prediction during the training. Okay, the prediction result will be generated during the training process. So uh, it is the method that we'll need after the network is trained to make prediction on the new data. Okay, normally if we want to predict on the new data, we use forward propagate. And then we can break the forward propagate into three parts, okay, which is the neuron activation, the neuron transfer, and also the forward propagation. Okay. And what is the neuron activation? Okay, neuron activation is actually the first step to calculate the activation of the one neuron given an input. Okay, the neuron activation. We have inputs. Okay, we have inputs, we have weight. Okay, now we have to calculate the neuron activation. Okay, so the neuron activation, example here, the neuron activation formula is similar as we did in the perceptron training. Okay, if you already watched the video that I uploaded last week, okay, we already went through the perceptron slide. If you don't remember this slide, okay, perceptron slide that I covered last week. Okay, in this slide we already learned about what is how can we calculate the net here. So same goes with this part, activation, which is the summation of weight. Okay, the summation of weight times input. Okay, you have to multiply weight multiply with input. Okay, so let's say you have four attributes earlier, right? So you have four attributes. So you have to, let's say you have one x, one input, two, you have four attributes. So you will have four inputs, and then you have four weight. Okay, weight one. Siapa yang tak silent tu boleh tolong silent. And weight 3 and weight 4. So you have to multiply input 1 with weight 1, input 2 with weight 2, input 3 with weight 3, and input 4 with weight 4. And then you have the value, and then you do the summation, tambah semua. Okay, the total. Okay, and then the total of the weight times the input plus the bias value. Okay, so weight is the network weight, input is an input, I is the index of the weight lah. It's either um, first input or second input. Okay, bias is a special weight that has no input to multiply with. Okay, so normally bias we put the bias value as 1. Okay, so that is for neuron activation. And the fourth part is the neuron transfer. Okay, for neuron transfer. So once you already activated the neuron, okay, the neuron, that means you do the multiplication lah, you do the calculation, input times the weight, right? So after that, you have to do the neuron transfer. Okay, for neuron transfer, that means we have to transfer the activation to see what the neuron output is actually is based on the neuron activation calculation. So different transfer function can be used. Okay. So, but normally in a traditional artificial neural network, we use the sigmoid activation function. Okay, as we learned in the previous lecture, okay, there are several kind of activation function, right? But normally we can use the sigmoid activation function. Okay, so for sigmoid activation function, this is the formula. The sigmoid activation function, it looks like S shape. It looks like this. That's the sigmoid activation function. So, to calculate the sigmoid activation function, we can use this formula. 1 over 1 plus exponents of negative x. Okay. All right. So forward propagating is an input and it's a straightforward. Okay. We work through each layer. Okay. Each layer, that means like we have input. Okay. We have input and then we have hidden layer. We have output. Okay. We work through each layer. Okay. And then to calculate the output of each neuron. It's a straightforward process lah for forward propagations. So back propagation training, it will use to train the networks. Okay, for back propagation, it's like for normal forward propagation, we move forward from input to the output, right? Back propagation, it goes backwards. Okay, it goes backward from the output to the inputs. Okay, to verify the answer that you got. Okay, so the delta here is the error. Okay, delta is referring to the error. Okay, this is the output. Okay, this is the hidden layer. Okay, this is the input. V is the weight for the input. Okay, when you calculate, you have to multiply these two, right? And then W is the weight for the hidden layer. So the same calculation. Okay. So for input, you multiply with the weight given to the input. For hidden layer, you multiply with the weight given to the hidden layer. Okay. So forward propagation, you see this solid arrow, it move forward. And then the dotted arrow here, it moves backward, is referring to the back propagation. So the back propagation learning process, we use error from output and propagate back to the previous layer for weight changes. Okay. So the goal of back propagation is to optimize the weight so that the neural network can learn how to correctly map the arbitrary input to the output. Okay, so how can we calculate the error? So error we calculate between the expected output. Okay, the expected output is the target lah. Okay, the target and the output forward propagated from the network. So target use given the target and the output that we actually get from the forward propagation, that's how we will calculate the error. Okay, so this error then be propagated backward through the network from the output layer to the hidden layer, assigning blame for the errors and update the weight as they go. Okay, so during the backpropagation process, they will also update the weight. Okay, so this part is broken down into two sections. So we have the transfer derivative and the error backpropagation. Okay, so the transfer derivative. For the transfer derivative, so let's say we have the output from the neuron, right? So we already went through the forward propagation. Okay, we went through the forward propagation and we have the output. We have the output here. We have output. So we need to calculate the slope of the output. So using the sigmoid transfer function, the derivative can be calculated as below. So we have the formula for derivative here. Output multiplied by 1 minus output. Okay, output multiplied by 1 minus output in order to calculate the derivative. And then after that, the second part of the backpropagation is error backpropagation. Okay, for error backpropagation, the first step is to calculate the error for each output neuron. This will give us our error signal to propagate backwards through the networks. So the output layer error is the multiplication of error value with activation function derivation. So you have the formula here. Okay, the formula to calculate the error. Okay, expected is the target lah, the target value. Okay, expected minus the output. The output is the actual value that we calculate from our input. Okay, times the transfer derivative output, transfer derivative from previous slide, from this slide. Okay, we calculate the transfer derivative. Okay, then you will get the error value. Okay, this is actually the whole formula to calculate the error lah. The delta symbols is referring to the error. Okay, so this error calculation is used for neuron in the output layer. So the expected value is the class value itself. Okay, all right. So the error signal for neuron in the hidden layer is calculated as the weighted error of each neuron in the output layer. Think of the error traveling back along the weights of the output layer to the neuron in the hidden layer. Because it says we have the error, okay, we have the error after the output, right? We have, this is output, and then we have the error that we calculate. And then this error value, it will travel all the way back, okay, and then it will pass the hidden layer, okay, it will update the weight for hidden layer, and then it will go straight to the input layer, and it will also updated the weight for the input layer. Okay, so the backpropagated error signal is accumulated and then used to determine the error of the neuron in the hidden layer. Okay, so once we updated the weight, okay, we calculate a new error. Okay, we have the original error here. We calculate a new error. Okay, with the weight k times error times the transfer derivative output. Okay. So error J is the error signal from the jth neuron in the output layer. That means the original error that we get from the output layer. Weight K is the weight that connects the kth neuron to the current neuron. That means whatever neurons, whatever attributes that you are working on right now, the weight for that one, okay, you have to do the multiplication. Okay, and output is the output for the current neuron. Okay, neuron ni, that means the flows lah, the flows of input hidden layer to output. Okay, input hidden layer to output, that's one neuron. Input hidden layer to to output the second neuron. Okay, So train network. After we did all that, we do the network training. Okay. The network is trained using stochastic gradient descent. Okay. So this involves the multiple iterations. That means you will have to do the calculation several times lah. So if you use Python, you can ask Python. You can set in your Python how many times to do the iteration. In the more iteration, the more accurate your results will be. Okay, so it involves multiple iteration of exposing a training data set to the network. And for each row of the data, forward propagating the inputs, back propagating the error and updating the network weights. Okay, it will, during the training process, it will keep doing the forward propagating, get the error, and then do the backward propagating. Okay, so this part is broken down into two sections, which is update the weight and the train networks. Okay, so to update the weight, as we learned in the previous lecture, the process for updating the weight is kind of similar lah. Okay, you plus WO is the all weight. Okay, and then plus the learning rate. Okay, the learning rate. Okay, same with the previous lecture. Okay, to update the new weight. Okay, all weight plus the learning rate. Okay, learning rate you can get based on your questions lah. Okay, based on your questions, learning rate will be given. Okay, so you just do the multiplication and then do the summation of the all weight plus the learning rate. Okay, and then the train network. As mentioned, the network is updated using stochastic gradient descent. Okay, this involves the first looping for a fixed number of epochs. And then within each epoch, updating the network for each row in the training dataset. That means it will update the network every epoch. So that means if you have 5 epoch, it will update it 5 times. If you use 10, if you set to 10 epoch, it will update 10 times. So because updates are made of each training pattern, so this type of learning is called online learning. So if errors were accumulated across an epoch before updating the week, this is called as batch learning or batch gradient descent. Okay, during the training process, right? When you trying to train data, okay, the more data that you included during the training process, the more accurate the process will be. Okay, normally for research, people will use 70% out of 100% data to be included as a training data. So let's say we have iris, we have, let's say if we have 100 data collection. Okay, we should use 70% of the uh, data to be training data. Okay, the more training data involved, the more accurate the results will be. Okay, these are the steps for the back propagation training. Okay, so you have input weight, you have the input networks. Okay, you have the input activation function. You after that you have to calculate. Okay, calculate the net hidden layer, activation function, the error, and the output layer. And then after you calculate, you have to update. Update the hidden layer weight. Okay, and then calculate the hidden layer error, and then we update the input weight. Okay, that's the step of the back propagation. Okay, this is the architecture lah, the architecture of the um, of the artificial neural network. Okay, this is input, this is weight, this is bias. Okay, uh, and then this is what output. Okay, you have to remember. Maybe it will be asked in the quiz next week. Okay, so any questions so far? The question? The question because so easy. so so if there are no questions, I will see you guys tomorrow for lab session. We will do the perceptron training. But perceptron training is already uploaded in Kalam. If you notice in Kalam, Dr. Hanis have give a detailed tutorial and also answers for the perceptron training. Okay, so tomorrow I'm just gonna go through the perceptron training steps. Okay, go through the answers that Dr. Anis have shared on Kalam together with you guys. Okay, and then I hope we can understand lah how to calculate the perceptron training. Okay, so if you guys have no questions, that's it for today. Okay, I will upload the video for the lecture and I will also upload the video for um, the back propagation tutorial. I will show you detailed back propagation tutorial. So there will be 2 video uploaded for today's class. Okay. So if there are no questions, I'll see you guys tomorrow during lab session to review the perceptron training. Thank you.
Okay, madam. Thank you.
Thank you, madam.
Thank you, madam.
Welcome.
Welcome.
Thank you, madam.
Salam.
Thank you, madam.
Macam
Thank you, madam.
Thank you,
Thank you,
madam.
madam. Thank you.